Okay, please open your notes if you haven't already. We're going to start with unit conversion today. So conversions between the same base unit can be as simple as using a decimal placement. Moving down the scale, you multiply by 10 for each step. Moving up the scale, you divide by 10 for each step. So when you write those two down, we'll talk about it. And then I'll get you this handout because I don't think you have this one yet. You all have this one with the bar across the top there? Okay, if you're looking at the unit conversion handout, the chart got like moved. It's supposed to be underneath the text, like right above where it says base unit, so that's why it looks a little wonky. But it says to convert SI units, you need to simply move the decimal point to the proper number of spaces. This is easiest done by writing out the units from largest to smallest, which is done in the box for you here. The blanks on the left are for the unit that you're measuring, and the blanks on the right is the prefix. When you wish to convert units, look at the direction and the number of spaces moved on the grid above. So if we look at the examples, it tells you the answers, but we have 100 centimeters and we want to convert it to what? We want to convert it to meters, right? So if your base unit is in the middle of the chart. And then if you go over what's the prefix? What's the letter for centa? The lowercase c, right? So if you start at C, you go back how many spaces to get to meters? 2. So if our decimal point was here, we would go back 1, 2, which equals how many meters? 1. Okay? And then if we have 0.05 kiloliters, and we want to go to centiliters, the lowercase k is right here. Can everybody find it on the chart? So how many spaces in which direction are we moving to get to the lowercase c? 5. 5, which direction? To the right. So we're going to take, we'll raise the kiloliters. 1, 2, 3, 4, 5. So we add 3 zeros. So 0.05 kiloliters equals 5,000 centiliters. That makes sense? How we did that on there? Okay. And you have this, correct? You already have this one?
Yeah.
On the back of this one, I think. Yes? No? Maybe? You didn't get that one yet?
I don't have it.
I thought I handed that one out last week. If I didn't, that's okay. I'll get it to you to make sure you have all of them, and I'll put extras up here. Everybody done with this slide? Okay, I'll get it to you because that has the prefixes on it, so you'll need it. Okay. So a few more on here. If we have 3.4 centigrams, C, G, which direction and how many spaces are we moving to get to grams? If you look at the chart, centigrams would be here, so how many places are we going? Back to the left, so we have 0.034. Easy enough on that one? Okay. What about microliters? Where are we going for this one? Where? How many from microliters to hectoliters? Anybody find micro on here?
Yeah.
Right here. So we're going back to lowercase what? H. So we're going 1, 2, 3, 4, 5, 6, 7, 8 spaces back, right? Next. Did I just 1, 2, 3, 4, 5, 6, 7, 8. Okay, so 0.00006, or if we write it in scientific notation, how many of you have written something in scientific notation before? Please tell me, all of you, I hope. Okay, so if we write that in scientific notation, we start with the 6, because we only have how many significant digits in 0.00006? 1, because leading zeros don't count. So we can write this in scientific notation with 1 significant digit times 10 to the negative. If there were a decimal here, how many times will we go back? 1, 2, 3, 4, 5. So 10 to the negative, because we're going backwards. That's a little preview because we're going to talk about scientific notation as a review. Questions about that? All right, what about 78 millimeters to nanometers? Where do we find the lowercase m on here? Is it on the right or on the left?
Right.
It's on the right. And then we're going forward, correct? We're going forward 1, 2, 3, 4, 5, 6 spaces. So 78. 1, 2, 3, 4, 5, 6. Or 78 million. So if we want to write that in scientific notation, because we only have how many sig figs in 78 million nanometers? We only have 2, right? Because do we have a decimal point down here? No. So just the 7 and the 8, just the non-zeros count because there's nothing that's trapped. So we write 7.8 times 10 to the 1, 2, 3, 4, 5, 6, 7. And then do we have the correct number of sig figs? Yeah, but does it still represent the same number? Yes. Any questions about that? Okay. So scientific notation helps us write really large numbers or really, really small numbers. An example is 3.4 times 10 to the 6th, which is the same thing as 3,400,000. I have a couple of these prefix charts left up here. Some of you need those. So terms written in scientific notation have 2 parts. There's the coefficient that must be a number between 1 and 9.9. No smaller than 1, no bigger than 9.9. And it has the exponent that is a power of 10. So in 3.4 times 10 to the 6th, which one is the coefficient? 3.4. And what's the exponent? 6. So you can label those if you will forget which one is the coefficient and which one is the exponent. Anybody need more time? So for numbers greater than 10, you find the number by moving the decimal point between 1 and 9.9. Sorry, not 1.9. So in the example, 45,300,000, the only number that you can create is 4.53. If you do 45.3, does that work? No, because 45 is bigger than what? What's the biggest number you can have for a coefficient? 9.9. Thank you. And then because you are moving to the right, you have a positive exponent. That wording is a little weird because it says that you move the decimal point to the left, and technically you did, but the positive number tells you to take 4.53 times 10 to the 7th and move the decimal point which direction? To the right or to the left? Which direction do you need to move it to get to 45,300,000? To the right from 4.53. You have to move it to the right. Anybody need more time with this slide? Okay. Okay, so for numbers less than 1, you do the same thing for the first part. You still have to create a coefficient using the number that's between 1 and 9.9 in your number. So in the example, 0.000291, the only number that you can create is 2.91. So that has to be your coefficient. And you're writing a negative exponent, which is equal to the number of places that you moved the decimal point to the right, but it's also the number of places that you would have to move it back in order to create the original number. And when you're done with this slide, we're going to stop here for today because tomorrow we'll be moving into calculator use and scientific notation. So we don't need to get those out today. We don't have enough time.